For Lab 11, Exercise F, we will be talking about the second half of this week's content. So we talked about humidity previously, and now we're going to be talking about atmospheric stability. Again, I want to point out that if the supplemental reading provided in the lab modules is not sufficient, you can always find more information about these concepts in your lab manual. Exercises 15, 16, 17 pretty much all cover atmospheric humidity as well as atmospheric stability. One thing that we need to remember before we really dive into understanding atmospheric stability is talking about air density. The denser that air is going to be, that means that there are going to be more molecules bouncing off of each other. The less dense that air is going to be, right, the higher up we get into the atmosphere, that means there are going to be less molecules bouncing off each other. We know so far that when more molecules are bouncing off of each other, there's going to be more friction, which means there's going to be more heat. So when we take a look at understanding atmospheric stability and how air parcels remain in place, or they rise, or they cool, when we're talking about the adiabatic pressure, or the adiabatic process, which we're about to get into, keep that in mind that warm air, if it is dense, has more molecules bouncing off of each other, making the air warm. Warm air is going to rise, and as that air rises, and we're just looking at the amount of pressure that exists in this air parcel represented by a balloon, as that air rises, the pressure decreases, meaning that this parcel is going to expand. And as that expands, the molecules get further and further apart, and there's going to be less heat generated because it is rising. So at some point, that air parcel is going to go up into the atmosphere, and it is going to cool. And eventually, that could cool to a point where it is going to start to sink again. So importantly, when we talk about an air parcel, and atmospheric stability, it really is just looking at what is going to rise and what is going to fall or sink, and whether or not our air parcel is going to be stable or unstable. Unstable air parcel, meaning that the air parcel is going to rise because it is warmer than the surrounding air. So it'll rise until it reaches the same temperature as the surrounding air. And as it rises, it will expand, lowering the amount of pressure in that air parcel, meaning it'll cool. A stable air parcel is an air parcel that is cooler than the surrounding temperature, meaning that it is not going to rise. And neutral air, or conditionally unstable air, is an air parcel that may become unstable due to other forces. And this may include wind, or this may include being forced over a geographic feature. So the adiabatic process, this is kind of what I was alluding to previously, is the cooling or warming based off of expansion. So the reason that air parcels become warm or cool as they rise and fall is not because there's some kind of heat exchange. Instead, they cool through the expansion, or they warm through compression. This kind of warming or cooling without an exchange of heat is called the adiabatic process. And so really there are two ways where we measure the rate at which this happens. We will have a dry adiabatic lapse rate or a saturated adiabatic lapse rate. And so it's important to note that an adiabatic cooling is going to be one of the only ways that a large mass of air or an air parcel is going to reach its dew point. And the lapse rate is the rate at which the parcel of air rises and cools. And so we have to keep in mind that there are two different types. Dry adiabatic lapse rate, meaning that there is less water vapor in the air, so there is no actual physical water droplets existing within the air parcel, as well as a saturated adiabatic lapse rate. So this is when that air is moist, when condensation starts and clouds can form. And when we get to the point where an air parcel condenses, meaning that water droplets are formed, that's what we call the lifting condensation level, the LCL. So that is when the altitude the rising air reaches its dew point. So as the air is going up, it reaches its dew point and goes from water vapor to actual water droplets forming clouds. So it reaches its saturation point, it'll condense, it reaches the saturation point because it is cooled, it condenses into clouds, and that is where you can see these clouds forming. This image does a really good job at showing that. So you can see that if the surrounding air has this temperature at every different altitude, right, 1,000 feet or meters, 2,000 meters, 3,000 meters, we can see that our air parcel, which is supposed to be represented by this little grayed out circle here, is showing that our air is roughly the same. But when the surrounding air becomes 19 degrees Celsius, our air parcel at 20 degrees is going to be warmer, causing it to rise. As the air parcel rises, it remains warmer than the air surrounding it. At some point, this dry adiabatic rate, so it is rising at 10 degrees Celsius for every 1,000 meters, it's going to reach that LCL, where it is going to reach its lifting condensation level. So the air parcel goes from just air vapor into condensation, it reaches that dew point, and you can see that this parcel of air is still warmer than the surrounding air. But notice how as soon as it has reached the LCL, the temperature is changing only at 6 degrees for every 1,000 meters. So from 10 to 4, it is going up, or it's going down 6 degrees. And from 4 degrees Celsius to -2, it is still dropping by 6 degrees. As compared to 10 degrees, and that is the difference between our dry adiabatic rate and our moist adiabatic rate. And so anytime you see this out in the wild, in the real world, where these clouds just happen to form at a specific elevation or altitude, this is why you're seeing this. It's the lifting condensation level. This is the point where that moisture in the atmosphere is condensing because it is reaching a saturation level. Keeping in mind we have our dry adiabatic rate and our moist adiabatic rate. We just talked about how the dry adiabatic rate changes temperatures at 10 degrees Celsius for every 1,000 meters. The moist adiabatic rate, right, that's when that parcel is saturated, is going to cool at 6 degrees for every 1,000 meters. So keeping that in mind, because this is also going to help inform us what or whether an air parcel is stable or unstable. If it is unstable, we know that the air parcel is going to rise. So the environmental lapse rate, or that is going to be the temperature of the environment or of the air surrounding our air parcel. If this is cooler than our air parcel, then we know that our air parcel is going to rise because it is warmer than the environment, the air in the environment, making it unstable because the air parcel is rising. And you can see these different lines are marking whether the air parcel is a dry adiabatic rate, so it is going at 10 degrees Celsius for every 1,000 meters, or if it is moist, it is rising at, or it is cooling at 6 degrees Celsius for every 1,000 meters. On the flip side, if our air is stable, that means it could still be cooling as it rises, but it will be warmer than the environment around it. So this air is going to be considered stable when compared to the unstable air. And you can see this image, or you can see this graph basically represented in this image again. If our surrounding air is colder than the air parcel is going to rise. We know that the environmental lapse rate cools at 12 degrees Celsius per every 1,000 meters. Our dry adiabatic rate is 10 degrees Celsius, and the moist adiabatic rate is 6 degrees. If the surrounding environmental lapse rate is 5 degrees Celsius, and our air parcel remains cooler than the environmental lapse rate, then it is not going to rise as fast and is going to remain stable or just may not rise at all. The environmental lapse rate is the actual decrease in temperature with an increase in altitude, again, of that surrounding air. And this is another really good image that tries to combine all of these different things. we have our dry adiabatic rate, our air parcel, which is being forced up in elevation because wind may be moving this over a mountain, will cool at 10 degrees for every 1,000 meters, 25 to 15. Excuse me. When this air parcel reaches its LCL, that's that condensation level, then we are going from a dry rate to a saturated rate or a moist adiabatic rate. And so we can see that the rate at which this parcel cools is going to transition from 10 degrees for every 1,000 meters to 6 degrees for every 1,000 meters. So 5 degrees minus 6 brings us to -1. Minus another 6 for another 1,000 meters brings us to -7. So this is showing us again how that rate of cooling changes based off of its dry adiabatic rate or its moist or saturated adiabatic rate. And so you can see how that transitions and how the temperature changes based off of the elevation and based off of whether or not that air parcel is dry or moist. This graph again quickly shows you the difference in an unstable air versus stable air. So when we're looking at our ELR, the environmental lapse rate, this is showing us what the natural environmental air around our air parcel looks like. So our air parcel is warmer than the environmental rate, so it is rising, making it unstable. On the other hand, if the environmental lapse rate or the environmental air is warmer, then our air parcel is less warm. It is going to remain stable. So how do we calculate this for our labs? So I know that, again, this is a ton of information to take in, so I really need you to pay attention to these following steps. Getting familiar with what the ELR is, the DAR, and the MAR is going to be really crucial to being able to understand the change in temperature and the rate at which that happens. So reading carefully, calculate the temperature for the environment, the environmental lapse rate, at the 3 following altitudes, point A through C. And we'll use an environmental lapse rate where the environment is cooling at 12 degrees for every 1,000 meters. Using the formulas below, let's figure out the 3 points. So we just need to subtract the ELR, which is going to be that rate of 12 degrees of cooling for every 1,000 meters for every elevation change. And you're going to have to plot these on the graph. So knowing that our change in rate is 12 degrees for every 1,000 meters, and we're starting at sea level, 0 meters, and our temperature is 25 degrees, we know that if we are going to go from 25 degrees, rise 1,000 meters at a rate of cooling of 12 degrees, you need to calculate for what that's going to be for point A. Take a minute, see if you can figure that out. You might be surprised at how simple this actually is. But you're right, it is 25 minus 12 degrees. So solving for point A is going to give us 13 degrees. So as we continue to rise in altitude, we have gotten to 2,000 meters. Our lapse rate, environmental lapse rate, is still 12 degrees. So we're going to do that again for point B, and then also try and figure out point C. So again, maybe pause the video, make those calculations so that you can test or see if you got the same answers that I did. Pause the video now. All right, let's check it out. Solving for points B and C, you can see that I've done my work, but if we have 13 degrees, subtract another 12 degrees because we've risen another 1,000 meters. That means that point B is going to be at 1 degree Celsius. Rising another 1,000 meters, still an environmental lapse rate of 12 degrees. Subtract that again, we are going to be left with a negative 11 degrees for point C. Relatively simple, as you can see that it is relatively basic subtraction as long as you can understand what we are looking at, that environmental lapse rate, that rate of cooling. So where it gets a little bit more complicated is when we start plugging in our dry adiabatic rate as well as the moist or saturated adiabatic rate. Most importantly, we know that that rate of cooling, 10 degrees per 1,000 meters, is different than that 12 degrees and is also different from that 6 degrees, which is the moist rate. So, reading from the top, calculate the temperature of the rising air parcel used in the previous question that has a vapor pressure, not saturated vapor pressure, of 9 millibars at three different altitudes. So we're going to solve for points W through Z. W has already been given to us because we know that the start, W, is going to be 25 degrees at 0 meters. Our dry adiabatic rate is 10 degrees for every 1,000 meters, and if we reach our moist saturation point, it's going to be 6 degrees for every 1,000 meters. So we now also have to pay attention to what is the saturated vapor pressure of our air parcel at 9 millibar vapor pressure. And that is where we're going to be able to jump back to this graph, which we used in the previous lab. So we need to figure out what air temperature our parcel has at 9 millibars. So going back over to looking at our saturated vapor pressure, we can see that any air parcel that has a vapor pressure at 9 millibars is going to become saturated when it hits 5 degrees Celsius. So as our air parcel is rising in altitude, it is going to cool at different rates, and as soon as that air parcel hits 5 degrees, we know that it has become saturated because the amount of vapor pressure in that parcel is 9 millibars. So let's go ahead and get this started. We know that rising from 0 degrees up 1,000 meters, our air is dry, so we are going to use our dry adiabatic rate. I have plugged this in for you, and we know that point X, this should definitely say X through C, but point X is going to be 25 degrees minus 10 degrees, and that is going to leave us with 15 degrees. So keeping in mind what our dew point, our saturated vapor pressure is, take a minute, pause the video now, and see if you can figure out what the other points are. So again, excuse me for this typo, but this should be points X, Y, and Z. Pause the video now. All right, let's see how you did. So we did this first one together. We got 15 degrees. And so we can now plug in our 15 degrees Celsius into X, and we know that we are still warmer than our 5 degrees Celsius. So our cooling rate is still going to be 10 degrees for every 1,000 meters. So 15 minus 10 is going to give us 5 degrees Celsius. And this should be the big red flag because we know that the vapor pressure for our air parcel is 9 millibars, and we can see that a parcel at 9 millibars, once it reaches 5 degrees Celsius, it is going to reach its saturation vapor point, its dew point, meaning that clouds will form. And that means that we are now at a different rate of cooling. Our moist adiabatic rate is going to be minus 6 degrees. So hopefully we understand how this connects here, because then we are going to take our 5 degrees as that air continues to rise, subtract 6 degrees from it across the next 1,000 meters, because we have gone from our dry adiabatic rate to our moist adiabatic rate, and that is going to leave us with negative 1 degrees Celsius. So again, keep in mind understanding the difference between the dry adiabatic rate, the moist adiabatic rate, knowing that warm air is going to rise and cool air is going to sink. And when you look back at whether a air parcel is stable or unstable, you have to compare to how it is cooling in comparison to the environmental rate. So keeping these graphs in mind, making sure that you understand exactly what you're seeing here, take a minute to read through them, read through all of the supplemental reading, and if that still isn't helping you, if you still have questions, please do not hesitate to reach out to me. So watch this video again if you need to. I believe you can do this. Let me know if there's any questions. Good luck.